Well, good afternoon, everyone. I'm Jason Gibson, CCO at IACMI. Innovation Insights is our monthly webinar series highlighting the people, ideas, and partnerships driving advances in composites and manufacturing across the U.S. As part of the Manufacturing USA Network, IACMI leads national efforts to scale new materials, develop sustainable processes, and strengthen U.S. manufacturing competitiveness. Now, before we get started, I'd like to mention that if you have any questions during our presentation, please enter them into our Q&A section, and we'll ask them to our presenters at the end of each section. At IACMI, our mission is to convene, connect, and catalyze. We convene the composites community to share ideas and opportunities, connect industry, academia, and national labs, and catalyze real progress through collaboration and commercialization. Today's Innovation Insights reflects that mission, highlighting new ideas, technologies, and applications driving the future of composites. For those new to IACMI, we accelerate composite innovation to strengthen U.S. manufacturing and workforce competitiveness through co-funded projects, access to world-class facilities, and a powerful national network. If you're listening today and you're not currently an IACMI member, we encourage you to consider the value of joining. When you become an IACMI member, you gain more than affiliation. You join a national network accelerating innovation in composites. IACMI gives you a platform to engage, contribute, and make an impact. We'd be excited to welcome you into our community, so please visit our website and reach out to us by filling out the online form. Now, one upcoming event I'd like to highlight as we get closer is our 2026 members meeting taking place in Denver, Colorado. This is a members-only event at no cost, and it's one of our best opportunities all year to connect across the IACMI network. You'll be able to network with nearly 200 member organizations, hear updates on our latest research and working group activities, and share what your company is working toward in the composite space. It's a great forum for aligning efforts, sparking new collaborations, and making sure your priorities are part of the broader conversation. Another event that's right around the corner worth highlighting is the SAMPI event taking place in Seattle in a couple of weeks. If you've never been, I highly recommend it. SAMPI is where the latest breakthroughs in advanced materials and composites move from concept to real-world application, bringing together industry leaders, innovators, and decision makers under one roof. If you want to see what's next in aerospace, energy, and high-performance manufacturing, and connect with the people driving it, this is the event you don't want to miss. Now, if this is your first time attending, we encourage you to explore past episodes that are available on our website. Since its launch, Innovation Insights has convened members and partners from across the composites ecosystems to share practical applications, emerging technologies, and lessons learned from active R&D and commercialization efforts. This series is designed to keep you current on industry trends while creating direct access to the people and the ideas shaping the next generation of composite materials and manufacturing technologies. And today is a good example of that. So, let me introduce our speakers. Today's Innovation Insights brings together presenters who are each contributing to the evolving landscape of nuclear energy from complementary technical and institutional perspectives. Their sessions span cutting-edge space nuclear technology, the current status of nuclear energy deployment in the U.S., and the historical foundations that continue to shape today's nuclear applications. So we'll begin today with Marc Gibson, Chief Engineer at Space Nuclear Power Corporation, who will present the company's work on developing a nuclear reactor for space applications. His session will focus on reactor technologies being designed to support future missions to the moon, highlighting engineering challenges, system requirements, and how space-based nuclear power can enable long-duration exploration. Next, Steve Zinkle, Governor's Chair for the University of Tennessee and Oak Ridge National Laboratory, will examine the renewed interest in nuclear energy technologies in the U.S. His talk will span the spectrum from traditional gigawatt-scale light water reactors to emerging small modular reactors and microreactors, highlighting their respective roles, deployment concepts, and supply chain considerations. The presentation will also outline potential applications of advanced composite materials in nuclear systems, including fuel forms, internal structures, radiation shielding, and concrete containment. And then last but not least, we'll close with Cliff Eberle. With over 4 decades of professional experience and 34 years of them at Oak Ridge, he's the perfect presenter for the history of nuclear research at Oak Ridge. His session will explore how many modern nuclear applications trace their origins back to early innovations at ORNL, including the original graphite reactor, and how that legacy continues to influence today's nuclear science and engineering efforts. So with that, I'd like to go ahead and turn it over to Marc for him to go ahead and start his presentation. Marc, feel free to share your screen.
All right, everybody see?
Yep, looks good.
All right, here we go. All right, again, my name is Marc Gibson. I'm the chief engineer here at SpaceNukes. SpaceNukes was founded by government experts in the space nuclear program that broke the paradigm of failed programs by executing the Duff and Krusty nuclear experiments. We left the government and started this company because the post-Krusty space reactor program was stalled inside the government due to lack of vision, funding, and some heavy bureaucracy. We see the long term as a commercial future, and our number one passion is to see our nuclear power technology enable the new space economy on the lunar surface, Mars, and in space power and propulsion missions for both commercial and government entities. So why nuclear in space? Nuclear allows us to bring our own energy source. People often refer to this as a nuclear battery. When you look at the energy density of nuclear, just one of our three core segments, as you can see in that left-hand picture that Dave Poston is holding, it's from our 1 kilowatt electric reactors, about 10.7 kilograms of highly enriched uranium fuel, equals the same energy as 121 fully fueled Falcon Heavy rockets. That's pretty crazy when you think about it. There's enough energy in our 32 kilogram core on our smallest reactor to power a kilowatt of electricity for a spacecraft for more than 100 years. So if you can imagine a Cassini-level deep space mission that lasts twice as long as the Voyager probes, that's the kind of energy we're talking about. So in addition to the Department of War, we see the market as three key segments: the lunar market, the Mars market, and the nuclear power and propulsion market. The lunar market, fission surface power is urgently needed to make Artemis real. Nuclear power is a necessity to build a permanent base and survive the lunar night using both heat and power. In parallel, commercial interests in mining, rocket fuel production, science, and industrial applications, abundant, reliable power is critically needed. On Mars, nuclear also makes a lot of sense. The dust storms that happen every few years make solar a risky proposition for human settlement. NASA switched from solar to nuclear-powered rovers for a reason. Water, a crucial resource, is not really available at the equator, but is abundant at higher latitudes where it's colder. For those interested in Mars, I always urge, especially the younger engineers, to look up the data from the Viking landers back in the 70s. It's publicly available, and you can see exactly what the environment like Mars is and to design to. I've extensively studied solar and nuclear power from Mars and nuclear winds and mass volume and infrastructure planning. That being said, the most reliable Mars power grid should employ both solar and nuclear power to reduce human fatality risks. There is no simple rescue missions on Mars, and power is life. On the third bullet, deep space science is another area where we spent a great deal of time working with the best mission planners and scientists in the world to capture a seemingly endless set of nuclear enabling missions. From ice-melting nuclear probes on Enceladus to Titan submarines to NEP vehicles that orbit multiple moons, nuclear is the key. All the deep space nuclear missions have been completed using RTGs, with the highest power being Cassini at 870 watts beginning in life. This provides a good baseline for what our 1 kilowatt reactor can do at a fraction of the price. Current RTG costs the government about $1 billion for about 100 watts of electricity, just to give you a feel there. So the proven technology, our kilopower reactor, the SpaceNukes team proved kilopower technology through multiple ground tests, including the Krusty experiment, which is the first nuclear test of a space reactor since 1965. Kilopower is designed for space, and Krusty was completed in a thermal vacuum chamber during this test to verify its operations in space. Terrestrial reactors, as you'll hear about today, have much different design requirements than space reactors. Terrestrial reactors have a more extensive safety and regulatory process, but space reactors have a much tougher requirements package related to mass, launch loads, higher operating temperatures, long life with no maintenance, and of course, the space environment. The no maintenance for long life is a real difficult piece, especially at the higher temperatures. The American Nuclear Society devoted a complete journal to the Krusty experiment for global peer review. As you'll know, peer review and benchmarking is extremely important because honest and experienced nuclear engineers extensively studied and reviewed our data and know that our reactor tech is very real and not just hype. Unfortunately, most of what you hear about today in the nuclear news is a lot of hype. Don't believe everything you hear until you see the data. As we say, show me the data, and it's reviewed by experts. Over a 3-year period, we designed, built, and ground tested the 1 kilowatt kilopower reactor rusty experiment for less than $18 million. We started SpaceNukes to finish and fly our kilopower technology because it's still the best solution for simple, safe, and reliable nuclear power. So what was Krusty? A lot of people ask. I encourage you to go to the website and read a lot about it. There's just way more information I can cover in this presentation. But as you can see in the picture, the left side is our spaceflight concept. In the middle there, or right to the right of that, is what we actually tested, at least the CAD models of it. You can see all the same components are in there, from the reactor core, the sodium heat pipes that transfer that heat from the reactor core up through the shield and up into the power converters. In this case, they were Stirling engines that convert that heat to electricity that powers the spacecraft. Over to the right is the actual hardware picture with some vacuum equipment around it. But you can see the similarities there, that what we fly is what we wanted to test. To continue that, you'll see in this picture on the left, this is the stacking of the HEU fuel. That's me actually putting the fuel into the heat pipes. The middle picture is where we're inserting our structural rings, where we heat them up, push them over the heat pipes, and let them cool down, and they do an interference fit to make sure that the heat pipes are constantly in contact with the core, because it's all about cooling the reactor. And then on the right is an inverted, the power system is inverted with the fuel on top still, and the power system on the bottom, and then a lot of facility equipment in between that you can't see the middle there. But that's the real hardware that went into the test. And what we accomplished was significant. This is just a couple hours of the testing. We completed a full 28 hours of nuclear testing at full temperature, full power, and then a space environment. The reactor closely matched the SpaceNukes modeling and proved the reactor would load follow as a Stirling power conversion system. The red line that you see is the actual reactor power reacting to the power conversion transient. So we increase and decrease the amount of electrical power coming out of Stirling engines, which also increases and decreases the cooling on the fuel. And on the top, you'll see the actual thermocouples of the fuel at about 800 C. And no matter what we would do to the reactor, it passively load follows that draw. So the dotted line that you see there is a control out position. We did not have to change the position. It's a completely passively physics-driven control system. So moving on, how do we use this technology that we've proven? So in order for commercially derived space nuclear power to work, we need to build multiple reactors that can be used in multiple missions. If you remember Henry Ford's slogan, you can have any color you want as long as it's black. This is the philosophy here. We need to qualify through extensive testing and achieve TRL-9 through the first flight. Mission 1, or serial number 1, as you see on the far left there. Probably going to be a nuclear electric propulsion mission is what it's looking like. We need to replicate the design in an assembly line aerospace manufacturing process to reduce costs and support multiple missions. The middle 3 pictures there you see would be like serial numbers 2, 3, and 4, supporting fission surface power on the moon, more nuclear electric propulsion for the government, and then collect reliability data through proven executed missions and continue to hone the manufacturing processes. This is similar to every other application that we do in aerospace. Apply the lessons learned to a new higher power design, rinse and repeat. So qualify the next power level, say 100 kilowatt system, go through the same processes and repeat. So why hasn't this been done before? It has, it just hasn't been done with space reactors. The 2 major challenges that have plagued the government programs are they keep changing their minds on power level and mission, which resets the development clock every few years. No programs have even come close to the finish line, except what we completed with Krusty while we were inside the government. And then the government's legally bound by the Federal Acquisitions Regulations to not order more parts than they need for any given mission. So private equity is needed to focus the resources, finish the product, and build multiple units for multiple mission infusion. Think of the launch vehicle suppliers today versus, say, 20 years ago. SpaceX, Falcon 9 are a great example. You pick a design and you perfect it. So Robert Heinlein was right. The moon is a harsh mistress, which innately favors nuclear. If you are not convinced about nuclear, spend some time and calculate the battery mass needed to provide just 100 kilowatts of electrical power through the 14-day lunar night. Then redo the calculation using the 400 kilowatts of thermal that the reactor provides. You'll quickly find out that the battery mass is enormous and nuclear power is needed. The lunar night is 2 weeks long, incredibly cold, down to 100 Kelvin in some spots. Strategic resources such as water and permanently shadowed regions. Because we carry our own energy density, our own energy source, we never have to see the sun. Most people don't understand that avionics and other electrical systems don't survive the extreme cold of the lunar night. In fact, all assets that NASA sends to the lunar surface only last up to 14 days. Hundreds of millions of dollars of assets die a frozen death after the sun sets without nuclear power. On the commercial side, industrial processes need significant heat, and nuclear provides approximately 70% of the reactor thermal power as waste heat. So using the waste heat from the power conversion system to supply a thermal grid provides over 90% efficient of the reactor power. The metric isn't watts electric per kilogram anymore, it's total watts per kilogram. Include the thermal as well as the nuclear. So we see the lunar market as an opportunity to build a nuclear-powered thermal and electric grid. The NASA FSP program has released several RFIs to get industry involved in the Artemis mission. 24/7 combined heat and power are game-changing resources that enable and protect lunar operations and assets. Commercial companies understand the importance of nuclear power. We have several letters of intent from commercial companies to buy metered power on the moon. Kilopower technology is perfectly suited to meet both the NASA Artemis and commercial needs for the moon. When you look at Mars, 42% less sunlight than Earth in orbit, what we call air mass zero, and yearly averages of usable solar power in the higher latitudes are closer to 20%. We've looked at the Mars missions extensively. As part of these trades, both internal to the government and at SpaceNukes, we found solutions with multiple 10 kilowatt kilopower units, all the way up to a megawatt design. Interestingly, using the Starship payload volume and innovative design solutions, the amount of power you can deliver isn't as dependent on the power level as you might think. We've been able to fit 35 reactors into the payload volume that reach a megawatt or a single megawatt reactor. Sending lots of power to the moon or Mars is more about the number of units needed at multiple locations to stand up a reliable grid. SpaceX would prefer to send 1,001 megawatt electric reactors, while NASA technical experts came to the conclusion that 4 10 kilowatt kilopower reactors was a great start for early human exploration and propellant production. The Mars market could be huge if Elon gets his way with his dream of 1 million people or optimized robots living on Mars. Starship is nuclear powered, but it needs a lot of energy to produce rocket fuel. So a lot of our studies was not only supplying power to help the human habitation, but create propellant, create fuel, oxygen, all the things that you need to not only live and survive, but to get back off the planet as needed. When we go to nuclear electric power and propulsion, while chemical rockets unlock travel to Leo, the moon, and Mars, the rest of the solar system will still be challenging without a network of propellant depots. Nuclear electric propulsion enables a true solar system exploration beyond all existing capabilities. The reactor-powered system provides electricity for the electric propulsion system that gets you to your destination. But once you're there, you can divert that power from the prop system to run a suite of science instruments and relay large amounts of data back to Earth. The 10 kilowatt reactor that powers the lunar base is actually the same reactor that powers the NEP vehicle, hence the multi-mission reactor. Multiple NASA studies have been completed to highlight missions that are enabled by NEP. If you want to read more, take a look at our website in our technical paper section. The latest paper, Kilopower, Nuclear Electric Propulsion for Outer Solar System Exploration, was a joint study by NASA, JPL, GRC, and Los Alamos National Lab to really study how enabling the fission power system for nuclear electric propulsion can enable missions. If you look at this chart, you'll see just as you get further away from the sun, the amount of energy that the sun provides is lower and lower and lower. As most people know, this is where deep space science really comes into effect. And when we're carrying our own energy source, we don't have to rely on that. So the market, traditional outer planet missions such as Cassini and New Horizons have been multi-billion-dollar missions. Plutonium-238 RTGs. Kilowatt provides 100x the power and a tenth of the cost. When applied to the Department of War, nuclear electric propulsion truly enables a maneuver without regret capability, which is not bound by the need for infrastructure such as propellant depots. And to quote Alan Stern, the principal investigator for NASA's New Horizons mission, fission is a game changer in deep space exploration. It will allow us to orbit Pluto the next time rather than fly by it. So the three key takeaways, nuclear fission is a game changer for the coming space economy, and it is coming. Our fission technology is ready now. We've completed all the major tests that need to be completed to have faith and reduce the risk in flying that reactor. And the timing is critical to deploy these systems this decade. If this presentation interests you, please feel free to reach out, whether you're a recent graduate looking for a job or a private investor looking for the next big win. We're happy to engage. And I will open it up for questions now.
Thanks, Marc. That was really good. So let me shoot some questions at you that came in.
Okay.
First one is, given the payload issues with getting a nuke on a spaceship, will Part 53 being finalized now make it easier to clear a reactor that may fit the space case easier?
So I think this is referring to launch safety. And I guess a lot of people don't realize that we design our reactors first and foremost for launch safety. Pat McClure is one of our founders. That's his expertise. And so the design is always wrapped around having a safe environment. We meet with flying colors all the new regulations as far as NSPM 20 and others. So yeah, I don't know if I answered that correctly because I didn't understand the 53 part, but the designs are started through with nuclear safety in mind. And the reactor does not turn on until we get to destination. So it's about I don't know, 10,000 times less radioactivity than an RTG on the launch pad. So it's much safer.
Thanks.
Mm-hmm.
Another question for you. Let's say Elon does end up at Mars and he wants to buy a nuclear reactor to do this, right?
Mm-hmm.
Is there other tested space nuclear power test beds that have been tested and validated, or your Krusty was the only one?
Yeah, Duff and Krusty were the only nuclear experiments to date, especially for space reactors. You're seeing a lot of the SMR folks take off here as they're trying to get testing done. I know they've been out at DAF doing zero particle critical testing, and as well, they're now at INL trying to get some of their powered reactor testing done by this summer. So we'll see how that goes. And again, those are small modular reactors for terrestrial use. They're not for space just yet. So yeah, we're the only ones that have tested a space reactor, and still the only ones that turn on a reactor at full power, a new reactor in, I don't know, the last 50 or 60 years. So, but it's coming. You can see that the pace has changed, and we believe that we had a major part in that by some of the work that we've completed.
Great, thank you. Well, appreciate it. In lieu of time, we're going to go ahead and move on to Dr. Steven Zinkle and his presentation. So if you'll stop sharing and let Steve share his.
All right, thanks.
Steve, we can see your screen, but you're muted. So if you're talking,
Yeah,
there you go.
sorry, it just took me a minute to find the right screen.
All right. Perfect. Looks good.
Okay. Yeah, so I'm going to talk about applications of advanced composites for nuclear. So as a way of introduction, there's been dramatic increased interest in small modular and Generation 4 fission reactors. There's something like approaching 50 companies that are pursuing various types of small modular reactors with greater than $5 billion in capital investments by private industries in the last 5 years or thereabouts. If you look at the historical record for light water reactors, the so-called capacity factor, the amount of watts out compared to what would be the ideal 24/7 operation. Light water reactors in the U.S. are truly the gold standard for utility scale electricity production, averaging over the last 25 years 90% plus capacity factors uh, year in, year out. And that makes them great interest for data centers and other applications. The flip side to this is that the technology for light water reactors is basically 1960s technology for a variety of reasons that it's frozen in at around 30 to 33% thermodynamic efficiency. So if you go back to 1960, when the first light water reactors were being developed, that was kind of in the ballpark with fossil energy, coal and gas were 35 to 38% or thereabouts. Over the ensuing decades, fossil energy incorporated new technologies, new materials, and was able to continuously improve on the thermodynamic efficiency, whereas light water reactors have been flatlined since that time. And this has led interest in so-called Generation 4 reactors, which are potential to operate at higher temperatures. So overall, if we look at the field for nuclear energy, there's three categories. There's continuation of the gigawatt electric scale traditional nuclear power plants. There's interest in smaller versions of those traditional nuclear power plants, but still using the same technology, light water reactor coolant. And then finally, there's interest in so-called Generation 4 reactors that would enable going to higher temperatures. And so in this slide of just showing an example on the left of a relatively advanced light water reactor version of a small modular reactor. And then on the right is an example of a high temperature Generation 4 concept that would be a different small modular reactor. If we can kind of compare the operating conditions for the core structural materials, the various colored boxes in this chart indicate what are the temperatures and the amount of atomic displacement damage that the materials would experience. So that's kind of their operating environment. The lower left green hatched region is the current experience base for traditional light water fission reactors. And so you can see that the Generation 4 systems are all operating at significantly higher temperatures, potentially better thermodynamic efficiencies. Also, most of them are also going up to much higher atomic displacement damage levels. So we would higher temperatures and higher atomic mixing from neutron collisions require more advanced materials. And so the key question is whether these new technologies with Generation 4 can approach the operational reliability that's been fabulous for the current light water reactor systems. If we look at operating sweet spot for potential ceramics in ceramic composite systems, the kind of the red shaded region indicates the sweet spot for operating silicon carbide. Turns out if you operate at too low of a temperature, you can introduce crystalline to amorphous phase transitions with an accompanying large amount of volumetric swelling on the order of 10% volumetric swelling for silicon carbide, as well as degradation in a lot of the mechanical properties. If you go to really high temperatures, you enter into another regime where it's a so-called void swelling regime that will tend to give also, with increasing dose, ever increasing amounts of dimensional swelling in the material. The Goldilocks in between region is you enter what is a a moderate amount of volumetric changes, and then it saturates after relatively low doses. And so that is, from a material science perspective, the desirable regime that you want to operate in. So if we look at potential applications for advanced composites in nuclear energy, I would say there's four key areas that come to mind. Um, Higher performance fuels, these would be based on the uh, tristructural isotopic so-called TRISO fuel systems, um, and variants of that, such as fully ceramic matrix fuels. I'll briefly talk about those in a couple of minutes. Um, and then there's various structures for in-core applications that could be ceramic reinforced ceramic matrix composites, whether they're fiber or particulate reinforcement. Um, Examples would be silicon carbide, fiber reinforced composites, etc. A third area is for radiation shielding with a variety of composites. And a fourth area is advanced concrete, which I'll briefly mention in a couple of minutes. So looking at advanced fuel concepts, the right-hand side is showing an example or a cross-section of a so-called TRISO fuel particle. It has a fuel kernel, and then a porous graphite layer, and then a silicon carbide pressure vessel layer, and then an outer graphite layer. In those multiple layers, the inner graphite layer can accommodate the fission gases that would be released during high burnups of the material, and then the silicon carbide pressure vessel keeps it from escaping out from that material. And so in traditional TRISO fuel systems, the high temperature gas reactors, the outer layer surrounding the fuel kernels or pellets are graphite composite material. Potentially, you could have better behavior by replacing the graphite with silicon carbide, and that would lead to a very high performance type of a system. But in general, this allows us to mix and match different optimized fuel cladding systems and different optimized fuel forms in the future. Many of the candidate ceramics are non-cubic systems, or hexagonal or other anisotropic systems. Under high fluence neutron irradiation, these systems are susceptible to grain boundary microcracking. A few examples being shown here, where you can see the pronounced cracking that occurs in these systems. And that's inherently due at this intermediate temperature regime that I mentioned previously, due to differential swelling along the different lattice directions in the grains of the material. And so in the case of graphite that's been heavily studied, at low temperatures, you can see very pronounced swelling in the C direction of the hexagonal close pack structure, and moderate dilatation in the A-axis direction of that material. And so this differential lattice swelling can introduce tremendous stresses at the grain boundaries of the material. If you go to higher temperatures, there's a tendency for an initial sintering of the material of a few percent, and then there's a turnaround, and then it goes into a rapidly swelling regime. The higher the temperature, the shorter the duration until it goes into this high swelling regime. From an engineering perspective, one can typically accommodate 5 to 10% of volumetric swelling in the material, but as you can see here, by the time we're reaching atomic displacement damage levels of 25 to 30 dPa, you would have unacceptably high volumetric swelling in the graphite. And this leads to significant cracking in the carbon-carbon composites that becomes progressively worse as you go up in temperatures. and leads to substantial degradation of the properties of the material, again, becoming increasingly worse as you go up to higher temperatures. If we move then to potential radiation shield material applications, lithium hydride has historically been a great candidate because of the low atomic number of the constituents, the hydrogen and the lithium in the material. Unfortunately, lithium hydride is susceptible to a process known as radiolysis that leads to rapid decomposition of the lithium hydride and can lead also with accompanying a large amount of volumetric swelling. And so this is even without neutron irradiation, just from gamma ray irradiation to moderate doses, you can exceed 10% swelling for temperatures up to about 300 degrees centigrade or so. And then at higher temperatures, there are other thermal decomposition issues with the lithium hydride. And so there's continuing research to look at alternative composite systems that may have superior performance compared to these monolithic systems that have been historically studied. Finally, I'll mention that there's potential applications for improved or advanced concrete systems. The degradation of a concrete that would be surrounding a nuclear reactor, it typically performs well for up to 40 years or so of operation. And then above that, some degradation has been observed in some nuclear reactors. In part, this is driven by radiation-induced volumetric expansion of the ceramic or mineral aggregates that are used in the construction of the concrete. This amount of swelling is dependent on the mineral composition. In particular, quartzite is relatively susceptible to this volumetric expansion. You can see 10 to 15% volumetric expansion in the case of quartzite, whereas marble or limestone are less susceptible to this volumetric expansion. And so if we look to the future of the possibility of factory build and then ship to site kind of construction methods, then you could use, rather than using locally sourced aggregates, which is the current standard practice, one could use radiation-resistant aggregates such as limestone, etc., for the construction of the concrete that would be shipped to the site. So to wrap up, I've just tried to very briefly introduce that advanced composites have a number of promising applications for future nuclear energy systems, ranging from the fuel systems, structural composites for within the core of the reactor, and then moving out as radiation shield, and then advanced concrete applications. Tried to highlight some of the potential disadvantages associated with materials that have anisotropic crystal structures for high dose applications. And in general, we have to be concerned or be aware of this amorphous to crystal phase transition, which depends at a critical temperature in the material. So with that, I think I'm right at time and would be glad to try to answer any questions there might be.
Great. Thanks for that, Steve. Question for you. So you mentioned the silicon carbide for applications of nuclear, and they've been looked at for fuel rod cladding. Typical fuel rod cladding is like a zirconium in nature, I believe, and there's an issue if you have an overrun in heat where the steam can interact and create a thermal overrun. Silicon carbide doesn't have that problem. What do you think is limiting the use of silicon carbide in fuel rod cladding in future applications? Is it a technology limitation, a capability to manufacture it, or cost, or why don't we see more silicon carbide fuel rod cladding out there is my basic.
So there are several contributing factors. Currently, the cost for fabricating the silicon carbide composites is substantially higher than for the zirconium alloy. So that's one consideration. Um, Ceramic matrix composites inherently contain some micro cracks, and so the hermeticity uh, of just a bare ceramic composite is not at the level that you would like it to be. So then you have to add an inner layer, a permeation layer, essentially on the material. So that further complicates the whole fabrication system. There's also under long-term exposure to boiling water reactor chemistries, silicon carbide, because of the high oxygen part per million levels in boiling water reactor chemistry, will slowly reduce to silicon dioxide on the surface layers, and silicon dioxide can dissolve in hot water. And so you get some dissolution of the silicon carbide during normal operating conditions. That effect is far reduced in pressurized water reactor chemistry water systems, but it's something that may require also introduction of a coating for very long-term operations of the system. So those factors in whole have limited the introduction of consideration of use of silicon carbide as an accident tolerant fuel cladding.
All right, that's very insightful. Well, I appreciate your time. Thank you for that. We're going to go ahead and turn it over to Dr. Cliff Eberle now for him to give us some nuclear history at Oak Ridge.
Okay, can you hear me and can you see my presentation?
I can hear you and see you. Looks good.
All right, let's see here if I can. Here we go. Okay, so I'm going to spend a few minutes talking about the nuclear heritage here in East Tennessee, and this is mostly focused at Oak Ridge National Laboratory, which is where the bulk of that is from. Uh, and A lot of people like to start a talk with a joke. I'm not particularly funny, but I did manage to run across this little cartoon about the birth of the nuclear navy dating back to the late 1940s. So happy hour in Oak Ridge, Tennessee, I guess was a good thing for us there. Uh, Hyman Rickover was the father of the nuclear navy, and he actually did some training in Oak Ridge in the late 40s. So um, the information sources here are several. There's a timeline at ornl.gov/timeline where most of this comes from. There's an account of ORNL's 13 nuclear reactors, and then a few things that I've dug out of my files or files of my friends. And this will be a very fast and quick tour. Um, so let's start with Oak Ridge's nuclear history. Starts with the Manhattan Project, the graphite reactor, which was the first continuously operating nuclear reactor in the world. Um, as I mentioned in the Manhattan Project, so it was a big secret when it started. And here on the upper right, you can see during construction, it's this area right here. And then we have preserved the logbook where the first criticality was reported at 5 a.m. on November 4th, I believe it was in 1943. Then here you can see on the lower left some operators that are either loading or unloading some experimental capsules. So, as I mentioned, Oak Ridge National Laboratory actually traces its birth date to the graphite reactor's first criticality, 5 a.m. November 4th, 1943. And that was an amazing accomplishment because the first proven nuclear reaction was at Chicago Pile 1 under Enrico Fermi's direction. That was December 2nd, 1942, I believe it was. So it was 11 months and 2 days, 337 days or a little less than 1 year from the time that it was proved you could actually have a controlled nuclear reaction until this reactor was designed, built, and went critical. It's an amazing accomplishment. And that reactor is a large portion of our nuclear heritage in Oak Ridge in East Tennessee in the United States. Obviously, its start was for nuclear weapons, but from that heritage, we have the blessings of neutron science, nuclear generated electricity, our nuclear navy, nuclear medicine, understanding of the genetic effects of radiation, and lots of our advanced materials and high performance computing also traces its origin to that reactor. Here is a little list of first. I believe that presentations will be posted, so I'm not going to go through these. Something that's dear to my heart is that the graphite reactor, it gets its name because it has a graphite moderator. This little award is for what was then the National Carbon Company. Today it's GrafTech, headquartered in Cleveland, Ohio, and they provided the graphite for that original reactor. And me being a carbon fiber guy, we trace our carbon materials heritage back to, at Oak Ridge, back to the graphite reactor and the graphite moderator. It was shut down on November 4th, 1963, exactly 20 years after the date that it first went critical. And then I'm going to go through a quick tour of different things through the years that have derived from the nuclear capabilities at Oak Ridge. The first thing was in the 1940s, we had the birth of neutron science. The first observation of the Bragg reflections and neutron diffraction were at the graphite reactor, and then they continued doing that work there. And that led to a Nobel Prize in 1994 for Clifford Shull. And today, Oak Ridge National Laboratory is the premier neutron science laboratory in the world based on that history. Quick tour, 1944, the pressurized water reactor. Oak Ridge was very instrumental in its creation, the original director, Alvin Weinberg. And that is today the basis of the nuclear navy in all commercial nuclear power reactors in the United States and around most of the world. 1946, we saw the birth of nuclear medicine, the use of reactors to actually generate radioisotopes that were used in the original nuclear medicine and continue today. We did a lot of work there in understanding radiation effects and protection, starting in 1946 into the 50s and well beyond. I remember whenever I went to work at Oak Ridge in 1984, at Y12, we had what we called the mouse house. There were about 250,000 mice. It was a continuing genetic strain. You could smell it all the way across campus, and that continued into the early 2000s. I believe that we no longer have that. But that was a big effort, was genetics, the genetics of radiation and how it passed from generation to generation through mutations. Here's one that relates to the very first presentation today. So there was a focus for a few years on nuclear powered aircraft. That went into the 60s, and we'll see a couple more things about that in a moment. And then the nuclear navy that was the first cartoon. So in 1946, based on its nuclear capabilities, Oak Ridge started a training program for many people in the United States, many engineers and scientists in the nuclear enterprise. U.S. Navy Captain Hyman Rickover attended that, and out of that, he actually sent a lot more Navy personnel back to that. He became the father of the nuclear Navy, and he based the nuclear navy, the light water reactor, based on work out of Oak Ridge, and he was the director of that from 1950 to 1981. But all of that was started at Oak Ridge. There were others, such as Idaho National Laboratory, then the Nuclear Reactor Test Station, that were instrumental in that as well. The nuclear technology really underpinned the computing at ORNL. Today, Oak Ridge National Laboratory is one of the world's leaders in high-performance computing periodically, and I believe currently has the fastest computer in the world. The computing expertise was initially to support the nuclear technology there. In 1948, the first nuclear electricity was generated. On the left, a really small steam engine there that generated enough nuclear electricity to power a flashlight bulb. And that was the first time that nuclear power was used to generate electricity. And then in 1952, the first electricity to the grid using one of the reactors I'll talk about in a little bit. And that was about 140 kilowatts sent to the grid. So it was a real amount. 1949, a lot of the initial work in nuclear reprocessing techniques, and those continue to be used around the world today. And then we also want to point back to nuclear for our advanced materials development. Today, it goes far, far beyond nuclear, but again, it was kind of the basis for the initial movement into advanced materials. There were materials for the nuclear reactors, and then there was the use of nuclear technology to do things like neutron transmission, transmutation doping for this technique for improved silicon. And Steve, I'll pause there for just a moment and ask if you'd like to add anything to this, since this is kind of where you live. Nope. Okay. We're going to make a quick tour through ORNL's nuclear reactors. It's had 13 nuclear reactors through its history. We already talked about the graphite reactor, world's first continuously operated nuclear reactor, operating from 1943 to 1963. The next reactor was the low-intensity test reactor, operated from 1950 to 68. You see a picture here, and that reactor showed water cooling feasibility. Then also starting in 1950 and operated until 1991 was the bulk shielding reactor. That really was the basis for many studies in radiation shielding. A lot of materials of radiation effects studies were done there. There were two what were called aqueous reactors, homogeneous, they call them the homogeneous reactor experiments. These used liquid fuel, uranyl sulfate dissolved in light water. The first one is the one that fed the 140 kilowatts of electricity to the grid. And then it was operated for a couple of years. And then the second one was operated for 4 more years and was used for corrosion studies, improved some of the designs and protocols for remote maintenance and repair within personnel exposure limits for nuclear reactors. I am not aware of any further aqueous reactors using liquid fuel after these two. Then also in 1954, the aircraft reactor experiment, we made a reference to that a while ago. It was a molten salt design using a beryllium oxide reflector, and it led to it only operated for 9 days or 10 days here, but it led to the development of several additional later reactors. This one goes along a little bit with the aircraft reactor, the one in the center. This is the tower shielding reactor facility, and there were two reactors operated there, or two Oak Ridge reactors, many others that were not Oak Ridge designed. The first was from 54 to 58, and then from 58, they continued to use it actually until 1992. The idea here was that if you were going to have nuclear aircraft, or I suppose nuclear, to a lesser extent, nuclear space, that you couldn't shield it with concrete or water or things like that. So this tower is hundreds of feet tall and hundreds of feet wide. You suspended the reactors on cables to do shielding experiments with those, and then whenever there was not an experiment in place, they would put it into a vault. So aircraft reactor shielding until 1961, and many other shielding studies up until 1992 when it was shut down. And as I mentioned, a lot of non-ORNL reactors were tested. There was something called the Geneva reactor in 1955. This was a showcase reactor for President Eisenhower's Atoms for Peace program, and it was sent to Switzerland, where it operated for until 1994. But it was only in the U.S. for a very short period. It was designed and built by Oak Ridge. There was a health physics research reactor devoted to understanding health physics and health safety in humans, operated from 1963 to 1987, focused on things like dosimetry, alarm testing, radiobiology, human body exposure and simulation, and weapon and accident spectra. In 1965, we started up the molten salt reactor. It operated for 4 years, and it demonstrated molten salt reactor technology for civilian power. and serves as the basis for several of the SMR designs that are currently in development. And it was the first reactor to operate using uranium-233. The Oak Ridge Research Reactor operated from 1958 until 87. So you can see a lot of these were like late 50s, early 60s, and into the late 80s or early 90s. This was for neutron scattering, did a lot of irradiated materials research there, and some radioisotope production. Then we get to the lone reactor that is still operating today. It is the high flux isotope reactor. It was built in 1965 and it continues operating today. Its original design was 100 megawatts. It has been derated to 85 megawatts. You can see to the left, the pool in the center here is actually the fuel element section. This was optimized to produce isotopes, and you see some things in the center. So the flux is highest in the center of the fuel element here. So that's where the isotopes are produced. It's also equipped with neutron beams for materials R&D, and it delivers one of the highest steady state neutron fluxes among the world's research reactors. And then on the right, you just see here a photo in the foreground. Down at the bottom is the HIFER complex, and up at the top is the lab's main complex. And I believe it's the rightmost one of those large stacks there is the graphite reactor. So we also have a long history in uranium enrichment. The lower three photos here. The one on the left is the K25 facility at Oak Ridge, and this site was closed in 1985. It's being reindustrialized today and is the site of some of the Renaissance that I'll talk about in a minute. Paducah, Kentucky, at the mouth of the Tennessee River, where it runs into the Ohio River, just a few miles from there. I actually personally worked there for about a year in the early 90s. And then that was the first stage of the enrichment, and then the Portsmouth, Ohio was the second stage. At Paducah, we went from 2 to 4%, from Portsmouth from 4% up to the terminal percentage. Composite centrifuges are how Oak Ridge National Laboratory got its start in composites. This is a fairly mature technology today. And is currently the sole commercial U.S. enrichment method and is getting a lot of attention. In January, DOE released $2.7 billion in task orders to expand the U.S. enrichment capacity. That was not designated specifically for composite centrifuges, but to the best of my knowledge, the bulk of it is in that area, with a little bit going to emerging laser enrichment technologies. Okay, let's talk for a moment. There's the nuclear renaissance ongoing that many of us know about. There are at least 2 reactors in planning in East Tennessee, one by TVA on the original Clinch River site, which is on the Oak Ridge Reservation, and then the other one is by Kairos Power. I believe both of those are on the Oak Ridge Reservation. I'm not completely certain about that, but I believe that is true. Oak Ridge, the manufacturing demonstration facility and the 3D printing capability have been doing quite a bit of work with Kairos Power on their reactor concepts, shielding concepts. Fuel supply chain is also important, coming back to the enrichment piece that we talked about a while ago. And so there is a TRISO fuel facility, recently received its NRC license for advanced fuel fabrication facility in Oak Ridge, and then Oklo is also working on an enrichment project in Oak Ridge. Other things include diagnostics, things like ways to monitor molten salts, ways to test nuclear capabilities for nuclear-powered rockets, and manufacturing capabilities, such as on the left here is a 3D printed metal rabbit capsule for use in a test reactor. So this is the kind of capsule that would go into the core of the HIFER reactor I showed a while ago, and work ongoing in things like how to accelerate siting of nuclear power data centers using high performance computing and similar capabilities. So that's a quick tour through the basics. I just want to mention 2 or 3 other things. So Oak Ridge has had a long history working on nuclear safety, computational simulation for nuclear performance and safety, supporting the safety. It hosts the CASTLE Consortium for the advanced simulation of light water reactors. Through the years, there's been a lot of work on nuclear non-proliferation, a lot of work in the area of robotics for working in radioactive environments. So basically, how do you do maintenance and repairs in hot cells without having to have humans in there? Uh, it has historically been involved in nuclear fusion research. I actually spent the first couple of years of my career, first 2 or 3 years in this space. And it has also been very involved in high energy accelerators. In fact, the lower right photo here is the spallation neutron source at Oak Ridge, started up in 2006. It is the world's most intense pulse neutron source. If memory serves me right, that's a 1 gigavolt proton beam, and it's a little over a megawatt in power. And I know they're working on a second target station there, which would be an extension, bring I believe it would use the same accelerator, but it would bring a second beam. And so that's a quick tour. So I'm open for questions.
Well, thank you for that, Cliff. I will say that we're past our time, so we're going to have to
Okay.
skip the question section, but if we missed any that we weren't able to get into, we'll be sure to respond to them later. But I want to thank everyone for their time. Thank you, everyone, for their presentations. It was very informative. Look forward to seeing everyone again next month on Monday, May 11th. But I appreciate it, and everyone have a great day.